The ocean is changing so fast that it may leave us behind, whisper some scientists who have spent countless hours studying the deep blue. Those words alone are enough to make anyone's heart skip a beat. What could be happening beneath the surface that triggers such dramatic caution? Today, we will plunge headlong into the most pressing oceanic crisis of our time. In this scenario, we will explore how human-induced climate shifts and rapidly changing ocean chemistry have pushed us dangerously close to waters unknown. We will untangle the hidden threads binding industrial carbon dioxide emissions, the subtle dance of marine life at every depth, and the very real threat that ocean acidification now poses to the future of our planet. By the end of this journey, you may find yourself asking, have we already changed the sea beyond recognition? And more importantly, we will look at how these transformations could reverberate through our own lives in ways that might surprise us. Imagine descending into a world where the water itself becomes a corrosive force. Yet that is not far-fetched hyperbole. The entire system of ocean acidity, once stable for millennia, is tipping into realms we never expected to see in our lifetimes. Here is the core issue we must address. The world's oceans have crossed a critical threshold known as a planetary boundary, meaning that the chemical change overtaking the waters may move us beyond the stable conditions of the Holocene era. You might wonder, how did we get here? And is it even possible to turn back? In this story, we shall chart the steady march of carbon dioxide into the air, its inevitable absorption into the seas, and the twisting consequences that affect coral reefs, tiny pteropods, and everything in between. In short, we will unmask the lethal spiral that could damage life on land just as much as it harms the dwellers of the deep. It might all sound devastatingly grim. Yet there is method in this story, and the ocean itself remains a wonder of resilience, for now. Leading experts, including Professor Helen Findley of Plymouth Marine Laboratory, have constructed a thorough map of how ocean chemistry has shifted across the globe. In collaboration with other oceanographers, marine biologists, and ecologists, she traced data from historical ice cores to modern computer models. Scouring evidence from as far back as the Industrial Revolution, these specialists concluded that ocean acidification has crossed a line once deemed safe. Specifically, the boundary hinges upon the saturation state of a particular form of calcium carbonate called aragonite. Countless marine organisms, from small mollusks to towering coral forests, rely on aragonite to build their protective shells and skeletons. That begs the question, what happens if that vital building block begins to dissolve faster than these creatures can regenerate? To properly illustrate the danger, let us acquaint ourselves with the concept of planetary boundaries. A few decades ago, scientists realized that Earth systems operate within certain tolerances. Once those tolerances are exceeded, we risk cascading destabilization in the climate, the biosphere, and the very cycles of life on which we depend. Of the 9 commonly accepted planetary boundaries, 6 were already believed to be breached. Among them, carbon cycle disruption, biodiversity loss, and rampant pollution. Now, there is a 7th, ocean acidification. This terrifying milestone was crossed around 5 years ago, quietly, insidiously, without headlines plastered across every major newspaper. The details are sobering. By the year 2000, the ocean's acidity had already shifted enough to cross the threshold. By 2020, well over 40% of the ocean's surface had drifted into a zone deemed beyond safe limits for many calcifying organisms. That revelation reveals a world in flux, but it is only half of the tale. Dive deeper, about 200 meters below the surface, and you find that 60% of those waters have also surpassed that crucial safety boundary. Why does this matter? Because an astonishing number of marine creatures live not just at the surface, but in the dark or semi-dark regions below. Here, shell-building species are not the only ones at risk. The entire chain of life in these deeper domains, small fish, cephalopods, sponges, corals, could become imperiled. Even large fish might struggle if their prey disappears or if the reefs they inhabit degrade. This sets off a domino effect that leads eventually onto our dinner plates and way of life. Now, if you imagine the typical coral reef in a sunny tropical sea, it is easy to see the flamboyance of life that might be threatened. But the transformations at work with ocean acidification are equally daunting in cold polar waters. Indeed, from the freezing northern latitudes to the edges of Antarctica, the ocean has become increasingly corrosive to creatures that produce shells and skeletons. Polar species, like certain plankton that serve as primary food sources for fish and whales, face the twin hazard of heightened acidity and warming temperatures, a combination that can stress them well beyond their capacity to adapt. Meanwhile, the ocean's ability to act as a carbon sponge is not infinite. When we emit carbon dioxide into the atmosphere, about 1/4 dissolves into the sea, where it forms carbonic acid and reduces the availability of essential carbonate ions. It might sound like minute chemistry, but the repercussions are monumental. Reduced carbonate ions make it tougher for oysters, clams, sea urchins, and even corals to build sturdy armor. Their enfeebled shells crack more easily or fail to grow at healthy rates, leaving them vulnerable to predators, disease, and environmental shifts. The overarching fear is that one day we might look back and realize, too late, that these critical links in the marine food chain have quietly crumbled. The question is, do we still have time to act? We have reached a dramatic inflection point in this story. Perhaps you are beginning to sense the urgency that oceanographers and marine biologists have been feeling for years, as they piece together data from remote sensors and ocean cruises that measure pH levels across the globe. It is worth pausing to absorb just how quietly these changes have swept in. When climate change is brought up, many people picture melting ice caps and violent storms, but the creeping sourness in the sea seldom takes center stage. Yet the deeper you investigate, the more alarm bells begin to ring. The rate of acidification is more rapid than anything recorded for approximately 55 million years. The Earth has indeed endured higher acidity levels in the ancient past, but never in such a short time frame, and never when we humans were so dependent on the sea's bounty. If you find these revelations eye-opening, please consider showing a little support for this deep dive. Your feedback helps shape future explorations into these critical topics. Underpinning this crisis is the notion that oceanic chemistry is intimately tied to all life on Earth, whether you live by the shore or far inland. For the fishing communities of the world, a collapse of shellfish stocks and coral reefs would be devastating, stripping away income streams and local culinary staples. On another level, these seas act as invaluable buffers against climate extremes, absorbing heat and providing moisture for weather systems the world over. If we push the chemistry too far, we chip away at the ocean's ability to deliver critical ecosystem services, such as coastal protection, carbon storage, and stable food webs. That begs the question, are we hurtling toward a future in which storms are stronger, coastlines are less protected, and seafood sources dwindle? What truly sets the work by Professor Findlay and her peers apart is their meticulous approach. They combine direct physical and chemical measurements spanning decades with data gleaned from ancient ice cores. The ocean's past is written in these frozen timelines, offering clues about historic greenhouse gas concentrations and temperature shifts that shaped marine life eons ago. By feeding these measurements into computer models, the researchers reconstructed how oceanic acidity changed from the Industrial Revolution through modern day. And the results were more unsettling than many dared to predict. By the turn of the century, in the year 2000, the ocean had already fallen below safe aragonite thresholds in vast stretches. In cold polar regions, where the saturation state has always been lower, that boundary has been crossed more dramatically. Even in subpolar waters and along North America's west coast from Canada to Mexico, the deeper ocean layers are revealing worrisome chemical shifts. From a purely practical viewpoint, ocean acidification also raises serious questions around how governments and organizations might respond. Is it feasible to roll out large-scale carbon dioxide removal technology? Could planting extensive seaweed farms help buffer nearshore waters by taking up carbon dioxide for photosynthesis? Or is the only truly effective fix the simplest but hardest path of all, rapid reduction in carbon emissions on a global scale? As you listen to these possibilities, remember that we are not merely protecting abstract marine life forms. We are safeguarding humanity's future security, nutrition, and resilience. Just when you think it cannot get any more urgent, new revelations arrive and push these challenges front and center. As you might guess, reversing ocean acidification is not as simple as flipping a switch. Even if we stopped emitting greenhouse gases this very instant, the carbon dioxide already in the atmosphere and seas would continue to drive a certain amount of further acidification. But the difference between cutting emissions now versus waiting another decade or 5 decades is enormous. By taking swift action, we can limit additional acidification, buy time for vulnerable species to adapt, and preserve the biodiversity that might one day hold medical or scientific breakthroughs. If you believe this issue deserves more attention, both in mainstream conversation and policymaking, go ahead and subscribe to stay updated on more analytical deep dives in the future. Being informed is the first step to forging collective action. We have examined the surface, the deeper waters, the polar threats, and the ramifications for fisheries and coastal communities. Yet one of the most disturbing angles comes from historical comparisons. Scientists emphasize that while the planet's oceans have indeed held higher acidity levels in the deep geologic past, specifically around 55 million years ago during the Paleocene-Eocene thermal maximum, those events occurred on geologic timescales. In other words, life had tens of thousands or even millions of years to adapt. Today, these colossal shifts are arising within mere centuries or even decades. That mismatch in timescales heightens the risk that many species simply cannot change fast enough. Consider the tiny pteropods, often called sea butterflies, that thrive in cold, nutrient-rich latitudes. These small, delicate creatures have translucent shells that show the harmful effects of acidification very quickly. In laboratory settings, lowered saturation states cause their shells to dissolve or grow weaker. If these tiny swimmers, a building block in the marine food web, collapse in population, the ripple effects can undermine entire marine ecosystems. Far from being an isolated problem, the plight of pteropods underscores how the smallest forms of life can wield massive influence over apex predators. Removing that foundation might cause a cascade that could gut entire fisheries and upend nutrient cycles. The question haunting many researchers is, how much can we break before we cannot fix it? The concept of planetary boundaries becomes painfully relevant here. Crossing such a boundary does not spell immediate doom. Rather, it signals that we are venturing into levels of pressure our planet has not experienced in stable epochs of human civilization. It is not identical to a tipping point, which implies a nearly irreversible cascade. Instead, it is more of an alarm to cease pushing our luck. The silver lining is that, according to Professor Findley, if we stop emitting greenhouse gases, we could theoretically reverse ocean chemistry changes over time. But the longer we wait, the more profound the ecological damage will be, and the harder it will be to restore balance or salvage critical marine habitats. The deeper waters are especially concerning for biodiversity. Though it is easy to focus on surface-dwelling species like clones, oysters, or corals that rely on sunlight, a vast community exists in the ocean's twilight realms, and even deeper. Eels, crustaceans, jellyfish, and hidden corals that form essential breeding grounds would also be impacted by creeping acidity. Research points out that, by the year 2020, over 40% of the surface had already become dangerously acidic. At 200 meters, that figure soared to 60%. If present trends continue, scientists predict that nearly 100% of surface waters could surpass the safe aragonite threshold by the end of this century, especially under moderate to high carbon emission scenarios. Faced with these startling trends, we see how the fate of marine life becomes inextricably linked to our own. If corals wink out of existence or pteropod populations plummet, entire fisheries might reel under the chain reaction. Coastal tourism economies reliant on vibrant reefs could watch in despair as these underwater landscapes turn into bleached skeletons. Communities that survive on small-scale fishing could see fewer catches and higher costs, leading to societal strain and potential displacement. Add to that the challenge of climate-enhanced storms battering coasts that are no longer protected by thriving reefs, and you can understand why ocean acidification is a global concern, not a niche environmental footnote. At this juncture, let us reflect on the bigger picture. Humans have enjoyed an unusual period of climate stability for thousands of years, what geologists call the Holocene era. This stable environment is where our civilizations took root and flourished. Now, with the dawn of the Anthropocene, we are tipping multiple planetary boundaries, and ocean acidification is confirming that we have ventured well beyond the conditions our species once took for granted. With these transformations accelerating, we must choose whether to remain passive observers or become stewards of the environment that sustains us. We cannot erase the greenhouse gases already released, but we can curtail further emissions, invest in sustainable practices, and do our part to manage local stressors, for instance by controlling coastal runoff, overfishing, and pollution. No less important is the fact that these changes are already measurable, not theoretical predictions in a vacuum. By painstakingly comparing data from modern observation systems, historical ship logs, and ancient ice records, scientists have drawn a timeline that highlights rapid acidification across the high latitudes and along certain coastlines. Regions that used to be refuges for cold-water corals or unique Arctic species are now at the forefront of these chemical transformations. As more carbon dioxide dissolves into the waves, the chain of life teeters from plankton to top predators. Marine scientists continue to sound the alarm, urging immediate cuts in carbon emissions if we wish to avoid scenarios that cause irreparable damage to oceanic ecosystems. One of the greatest wonders in all this is the ocean's capacity to bounce back if given enough space and time. Some coral species exhibit a degree of resilience, especially if water temperatures remain within acceptable ranges and local stressors are minimized. Seaweed forests and mangrove wetlands might help sequester carbon, offering a buffer for nearshore waters. But these solutions are not miracles that can reverse decades of relentless emissions overnight. Instead, they must be complemented by comprehensive shifts in energy use, political will, and cultural mindset. We must swap short-term profit motives for long-term planetary stewardship, encouraging global cooperation on mitigation strategies. With the threads of this narrative weaving together, pause to consider where you stand in the grand tapestry. Do you live in a coastal region that could experience powerful storms and erosion if coral reefs die off? Do you enjoy seafood that depends on a delicate marine chain? Or are you in an inland city, reliant on stable climates and distant ecosystems? Regardless, ocean acidification could touch your life in tangible ways, altering everything from the cost of fish in local markets to the severity of storms that roil faraway coastlines. The science is sobering, but it also suggests that by acting quickly, we can avert some of the worst-case scenarios. If you have been immersed in these insights so far, please remember to like this segment. Small acts of engagement help spread the word about these urgent environmental realities. So, where do we go from here? Professor Finley herself points to the need for both high-level international agreements and grassroots action. Policymakers must recognize that ocean acidification is as critical as temperature rise. Both are consequences of carbon pollution. Efforts such as improved marine protected areas, emissions regulations, and innovative research funding can tip the scale back toward a safer realm. Education is another cornerstone. The more people learn about ocean chemistry and how intimately it intertwines with everyday life, the stronger our collective push for meaningful change. Another tool is developing early warning systems to detect chemical changes in vulnerable hotspots, giving local communities the chance to adapt. The ocean, contrary to popular belief, is not an everlasting reservoir of forgiveness. Yes, it sops up carbon emissions with staggering efficiency, but that generosity comes at a price. The formation of carbonic acid quietly gnaws away at all things that rely on calcium carbonate. And as we have seen, the downward spiral has broader implications for entire ecosystems. Yet we must remember that while crossing a planetary boundary is an ominous sign, it is not an eternal condemnation. The big difference between a boundary and a tipping point is that the boundary highlights the edge of a safe operating space for human civilization. Once exceeded, it signals that the risk of irreversible changes surges. By halting or drastically reducing greenhouse gas emissions, there is still a pathway to guide the oceans away from catastrophic outcomes. The question is, do we have the collective will to do so? In the final analysis, these revelations about acidification, the plight of delicate shell-building creatures, and the potential unraveling of marine food webs must not be brushed aside as mere academic concerns. We stand at a precipice, with glimpses of a future ocean that might be radically different from the one we have known. Deeper waters are becoming dangerously acidic, polar regions are vulnerable, and even heavily populated coastal areas could face unwelcome surprises if current trends continue unabated. This scenario may not be comfortable, but it paints a truthful picture of what is at stake. Will we learn from the science, or let this crisis worsen? In telling this story, we have traveled through time, back to Eris 55 million years ago, when life endured massive shifts, and forward to the next decades, where every ton of carbon emitted may tip the scales further. We have spoken of shimmering coral reefs that could turn desolate, of tiny pteropods valiantly trying to hold on to their fragile shells, and of fisheries struggling to cope with changing waters. Through it all, one point emerges with clarity. The ocean's fate is inextricably linked with our own destinies. Our blue planet offers immeasurable value: food, livelihoods, weather regulation, cultural inspiration. But it is up to us to decide if future generations will inherit seas teeming with vibrant life or seas tipping toward collapse. Let us not rush headlong into the unknown. Instead, let us harness scientific wisdom, collective will, and urgent policy changes to steer our grand ocean realm back to safer waters.